Welcome to Academia Sinica Lecture today. We are very happy to open in this lecture with the opening remarks by Dr. Qi Wong, the President of Academia Sinica. Now let's welcome President Wong.
Ladies and gentlemen, it's my great pleasure and honor to introduce this year's Academia Sinica Lecture, Professor Cicerone. Professor Cicerone is currently the President of National Academy of Sciences of the United States and Chair of the National Research Council. He is an internationally well-known, distinguished atmospheric scientist. Beyond his scientific achievement, Dr. Cicerone has been also a leader in the international community of atmospheric chemistry, earth environment, biogeochemistry, and global changes. His scientific work has helped shape science and environmental policy at the highest level, both nationally in the United States and internationally. Throughout his research career, Dr. Cicerone has received many awards and honors in recognition of his scientific work. The Franklin Institute recognized his fundamental contributions to the understanding of greenhouse gases and ozone depletion by selecting him as the 1999 laureate for Bauer Award and Prize for Achievement in Science. The prestigious Bauer Award also recognized his public policy leadership in protecting the global environment. In 2001, at the request of President Bush, Dr. Cicerone led the National Academy of Sciences a study of the current state of climate change and its impact on the environment and human health. The American Geophysical Union awarded Dr. Cicerone its 2002 Roger Berry Medal for outstanding research and contribution to the understanding of atmospheric processes, biogeochemical cycles, and other key elements of the climate system. In 2004, the World Cultural Council honored him with the Albert Einstein World Award in Science, one of science's most distinguished awards. Dr. Cicerone is a member of the American Academy of Arts and Sciences, the American Philosophical Society, and the National Academy of Sciences. He is a proud member of the National Academies of many countries, including Italy, Russia, Korea, Spain, and UK. And I'm very proud to mention that Dr. Cicerone was elected honorary member of Academia Sinica in 2010. Dr. Cicerone was educated at the Massachusetts Institute of Technology, where he received his BS degree in electrical engineering. And at that time, I was told that he was also the captain and a teacher of the baseball team at MIT. And the University of Illinois, where he got his PhD in electrical engineering. He began his research career at the University of Michigan, where the Ralph Cicerone Distinguished University Professorship of Atmospheric Science was established in 2007 in his honor. Dr. Cicerone continued his research at the Scripps Institution of Oceanography at the University of California, San Diego, and at the National Center for Atmospheric Research in Boulder, Colorado. In 1989, he joined the University of California, Irvine, where he was the founding chair of the Department of Earth System Science and the Daniel Aldrich Professor of Earth System Science, Dean of the School of Physical Sciences, and Chancellor immediately prior to his election as Academy President in 2005. Dr. Cicerone served on the Secretary of Energy's Advisory Committee, and he's a trustee of the Canadian Corporation of the World. Professor Cicerone will give 2 lectures during his stay in Taiwan. The topic of his lecture today is global climate change caused by greenhouse gases from human activities. His second lecture, entitled Protecting the Ozone Layer, was easier than stabilizing Earth climate. The second lecture will be delivered tomorrow at the National Taiwan University. So before Professor Cicerone give his lecture, I would like to invite him to come up to the stage to receive the honorary academician medal and also a special gift to honor him as the Academia Sinica Lecture.
Now, President Wong is presenting the honorary academician badge and the crystal award to Dr. Cicerone. Please give a big hand to welcome him. Now, President Cicerone is going to start his presentation.
This headset is so that I do not have to listen to myself. Thank you very much, President Wong, for that very kind introduction and for the nice memento of this occasion. It's an honor to be here today, to see so many of you from Academia Sinica and high school students as well. Thank you. The topic of global climate change is a very important one, and it's going to stay with us for a long time. What I'm going to do today is to give a very quick review of the physical principles that are at play here, the greenhouse effect. And then I'm going to spend most of the time available to discuss what we are measuring, that is, actual observations from the air and the water and the ice masses. And I'm going to show you a lot of data on slides, and then I will try to present some of the evidence that convinces us that we are dealing with a human cause, the changing of the world's atmosphere by human activities, and then just close with a few words about what we should do next. However, I'm not going to talk today about the responses of humans, how we can control the situation or stabilize it a little bit, but if we have time for discussion afterwards, perhaps we can go into it then. So this is an outline of what I would like to talk about. First, as I said, a brief review of the physical principles at play, the greenhouse effect. Then I will spend most of the time on observed trends, that is, actual measurements in several of the key climate variables. And then I'll present some of the evidence about human activity toward the end. First of all, this is just a simple statement of the fact that the energy balance of the planet Earth largely controls the global climate. You can actually see this on individual days and nights. When the sun is out in the daytime, it gets warmer, and if it's a cool, clear night, it will cool off at nighttime. so that in some sense you can see that the energy coming in from the sun and the energy escaping from the Earth at night are controlling the temperature. That observation, while it's not tremendously scientific or profound, I think it is profound, even though I'm not putting any numbers on it. But that energy balance also applies over long periods of time, 10,000 years or even 100 million years. So I'll try to be a little bit more quantitative. This diagram is like a cartoon, but there is some reality to it. The energy coming to us from the sun is mostly in the form of visible light and near-infrared radiation. And if you average over the entire planet, day and night, it's about 340 watts per square meter, averaged over day and night in every place on the Earth. Now, the Earth loses about 239 watts per square meter that goes back to space in the form of infrared radiation. And of this 341 that comes from the sun, about 102 watts per square meter is reflected immediately as visible light from the tops of white surfaces, like snow and ice cover the tops of clouds. So generally speaking, the planet's energy is in balance. We know that the Earth is not heating up very rapidly, nor is it getting cold very rapidly, so that these two figures more or less balance. In reality, we now have evidence that the Earth's energy is no longer in balance, and I will show you some of the evidence. This outgoing heat from the planet, though, in the form of infrared radiation, can interact with what is in the air, gases like water vapor, carbon dioxide, ozone, and many others. So that is one of the bases for how we could change the planet's climate by changing the chemical composition of the air. Now, there's a reality to this. We can calculate what the temperatures are on other planets. And for example, for Mars, we can calculate, and I'll show you how we do that, and we find the right answer. It's about, well, that is about the right answer, minus 28 degrees centigrade. The way we do it, though, is if S means the incoming sunlight from the Earth, measured in energy units, and we multiply by the amount that's absorbed, that is 1 minus the amount that's reflected, it can be equated to, in steady state, that is no time differences, no time changes, to the Stefan-Boltzmann law of radiation, a constant times temperature to the 4th power. So this quantity is measured, this quantity is measured, this quantity is a physical constant, so we can calculate the temperature of the Earth. And from this calculation, then we can do the same calculation for Earth, Mars, and Venus. And for Mars, we obtain the correct answer for Mars. It's because Mars has a thin atmosphere, very little air in it, and it's essentially what I said, the incoming radiation is balanced by the outgoing infrared. But for Earth, when we do the same calculation, we calculate that the Earth is frozen solid, minus 18 degrees centigrade, which is minus 32 Fahrenheit, and it's wrong. And the reason that this calculation is wrong, you can demonstrate, is that there is a natural greenhouse effect for the Earth by the air and the substances in the air, and also clouds. For Venus, the calculation is worse. We calculate that the temperature of the Venus atmosphere is similar to that for the Earth, when in fact it's several hundred degrees centigrade. Venus has what is known as a runaway greenhouse effect. It has an atmosphere which is nearly 100 times more dense than the Earth's, and it has many greenhouse gases and clouds in it. So you begin to realize that this statement that the greenhouse effect, it's real. It's a natural phenomenon. We have evidence of it. In fact, one of the first satellites that ever orbited the Earth for scientific purposes flew in 1971, and it looked down at the Earth in the infrared wavelengths, and it measured the outgoing radiation at the infrared. Now, if the Earth were an ideal black body radiating at 200 Kelvin, this is what the graph would have looked like at infrared wavelengths. Or if it were 300 Kelvin, which is obviously 27 centigrade, the curve would have been like this smooth dash curve. In reality, looking down at the tropical Pacific Ocean, where the temperature is perhaps 288 or 300, instead of being a smooth curve like this, instead it had all of this structure in it, which represents the energy trapped by carbon dioxide, by ozone at about 9.6 micrometers wavelength, a carbon dioxide 15 micrometer feature, and so forth. So you can look at the Earth and see the evidence of the greenhouse effect. This was, as I say, back in 1971, so the human causes had not yet become as dominant or as big as they are now. So the basis of this concern that we have now about climate change is that we can measure what's in the air, and this is a beautiful set of measurements now of carbon dioxide in the atmosphere as a fraction. So when the measurements started in late 1957, the initial concentration was around 315 parts per million, and over the years it has grown to nearly 400 parts per million now in 2013, 2014. However, there is an annual cycle. I should explain, each one of these black dots is the average of it over a month, with measurements taken about every hour, so that every black dot is a monthly average. And in the springtime every year and the summer, the CO2 concentration is low, and then in the next autumn and winter it rises, falls, rises and falls every year under the influence of photosynthesis, taking carbon dioxide out of the atmosphere, and then respiration and decay happening in the autumn and winter time. And the closer you are to a land surface, the deeper this annual cycle is. If you would look at the same data for the South Pole, there is virtually no annual cycle because the air nearby is not in contact with living, decaying, and photorespiring things. But the main message is that the carbon dioxide amounts have grown so much. And I'll show you some evidence a little later on why we're really certain that this is due to human activity. So there are many other greenhouse gases, and I'll mention a few of them today, but this is just to get started. Now let's go to some actual data on the heating and the other changes in the Earth. There are many different observatories around the world that are measuring temperature. These particular data are from a NASA group, and 0 on this chart is not 0 degrees centigrade, it's a reference point. It's the average of what was observed over the entire world in this 30-year period, 1950 to 64. So this is to 80, 1950 to 1980. So 0 is the average of this 30-year period. Anything negative means that the temperatures were lower than in 1950 to 1980, and then anything above that level is the warming since. The data start in 1880, which was the beginning of the use of thermometers in enough places around the world to construct a proper global average. And in this graph, there are probably 500 million temperature measurements represented. So, starting back before 1900, the green vertical bars are the statistical uncertainty of the measurements, and they were a little bit rough. You'll see the size of the green bars getting a little smaller as we go along with better data sets and more data. Generally speaking, there might have been a little cooling before 1900, but it's not clear that that was very meaningful. It probably was. Then a warming until about 1940, and then a slight cooling until about 1975, and then ever since then, more or less, a warming. I want to show you a few more aspects of these data, though, to give you a feeling of what is available. These are the same data now divided into Northern Hemisphere, above the equator and southern hemisphere in blue below the equator. And you'll see that they do not move completely in a correlated or lockstep way, although generally you can see the same kind of a warming until about 1940, but with big statistical uncertainty. And then both northern and southern hemisphere warming since about 1980 or 1975. But here you'll see that the southern hemisphere is cooler than the northern hemisphere the last 20 years or so. These years which were cold in the northern hemisphere were record high years in the southern hemisphere. But that kind of behavior is similar to what you would expect, because south of the equator we have twice as much ocean as we do north of the equator. So the southern hemisphere, if the planet is warming, you would expect the southern hemisphere to warm a little more slowly. And that's the kind of thing you see here. I want to break these data down a little further into a two-dimensional plot. So this is the equator running across the middle, the Arctic region, the Antarctic region, and we're showing 3 different years here. The current year, and this is only the first 2 months, January through February. You'll see that the false color chart down here shows that the Arctic is really much warmer than that 30-year period I showed you, 1950 to 1980. And the Arctic in every one of these years, 2005, 10, and 14. And these years are chosen because they have been recent years that were also much warmer than normal. All of the recent years have been much warmer than normal. Although in January and February of this year, you'll see that the east coast of the United States was very cold, and this is causing people to talk now about how climate change is not happening, and it's just a very false claim. Generally speaking, though, over the last 50 years or 40 years, the Arctic regions are warming much faster than anywhere else on the Earth. There are virtually no places where it's colder than normal. In fact, if you were to average, let's say, the last 10 years, you would find no appearance of these blue and light colors at all. The entire world is warming. And then this is a monthly record just showing how the months have gone. For example, the record high year before this year, the year 2005, this is the way the months of the year went, January, February, and so forth. And this year, it started out with a hot January and then a very cold February worldwide. So this, once again, this is to give you an idea of how much work is going on with these temperature data. Now, this chart is, to me, very stunning. It shows the 10-year statistics. So starting with the decade of 1951 to 1961, in this kind of normal distribution, then going to the next one, 61 to 71, and so forth. The point is, every decade is moving to the right on this chart. Now, the technical aspects are, this particular graph is for northern hemisphere land areas only, June, July, and August, so summer months in the northern hemisphere. And the vertical axis is the frequency at which a given temperature is being observed, and the temperature is the anomaly, that is the difference between the temperature that's being measured and the 30-year average, measured in units of standard deviation. So this is like a Gaussian curve with a certain standard deviation, and the shape of the curve is staying the same, but it's moving to the right. So you can see that the decade that we're, the 2001 to 2011 decade is already more than 1 standard deviation to the right. And look at the probability tails here, if you will, frequency tails. The ratio of this color to the earlier decades is about a factor of 4 or 5 higher if you go out to 4 standard deviations. Or if you go out to 3 standard deviations, it's even more. It's a factor of 5 or 6 higher. So extreme events are happening on the high side. That is, we're getting many more hot days than we used to. There is still a probability of getting cold days, but it's moving towards heat, basically. Well, a few years ago, over the last 15 years, there have been people who are very skeptical of these results, making all kinds of claims that satellite measurements do not show the same thing. Fortunately, the errors have been found in the satellite measurements, so this thermometer record is what you would expect. It's very good. There were other claims that, well, the temperature record is not of uniform quality, that there might be some stations where the temperatures are being measured which are not high quality. So one group of scientists, perhaps Professor Lee knows these people. I'm sorry, this is a group out of Berkeley led by a physicist, Richard Muller, who had made these claims that these temperature data which I've just been showing you are not reliable. For example, they had photographs of certain meteorological instruments that had rust on them. They were not being maintained. There are other meteorological stations that had been built in the outskirts of a city, and then the city grew so that the station is now surrounded by a city with blacktop all around and so forth. So this group at Berkeley did a very good job. They took all of the data they could get from everywhere, going back to actually even earlier in time, but let's say the recent record from 1880 till forward, and they found that it basically didn't matter what they did with those bad stations. They also corrected the data for the population and heat generated by the nearby cities. And they've ended up with the same record that I just showed you from the NASA group and the group in England and a couple of other places. So that the robustness, the reliability of these temperature data sets that people are working with has now been tested in several ways. And I think this set of results from the Berkeley Earth Surface Temperature Project I think helped to show people that. Now let's switch to oceans. The oceans are getting warmer, and we've known this for probably 30 years, but only in the top 700 meters or so. So this graph shows depth going down into the ocean. The surface is 0, 200 meters below, all the way down to 2,000 meters below the surface of the ocean, with ocean heat content measured on the x-axis. And this is a 55-year period, 1955 to 2100, by combining the very sparse data sets from all over the world's oceans, Pacific Ocean, Atlantic, Indian, and so forth, showing that the world ocean on average has a higher heat content now than it did 55 years ago, with fairly smooth curves. And the next graph is similar, but I think easier to understand. This graph now lumps the 700, here we are. This is the one I want. 0 to 2,000 meters is this red curve showing that a fair amount of heat measured in, let's see, what is it? Heat content measured in 10 to the 22 joules has increased with time in the world's oceans down to 2 kilometers depth, and from 0 to 700 meters, or no, this is 700 to 2,000 meters, there's a smaller amount of heat buried. So there's clearly evidence now that heat from the air is flowing down into the world's oceans. It's not clear whether that's due to thermal conductivity alone or whether it's due to turbulent transfer, and I think the right answer is both. And it's hard to get good average data, but you can now do a calculation of exactly how much heat the ocean has absorbed compared to how much the greenhouse forcing is putting there due to the increase in the greenhouse gases. And that calculation is based on laboratory spectroscopy, which is very, very good data on these greenhouse gases. And you get a pretty good agreement, so that it looks very much like the picture that we're describing, namely the perturbation in the energy balance of the Earth, is now measured quantitatively, and we can see where the heat is going. Let me show you a different kind of evidence. Sea level rise. I know that you're very well aware of where the sea is here in Taiwan, but people have been measuring the sea level very carefully for well over 100 years in a very primitive way, going back to 1880 and 1890. Very primitive measurements, but being done very carefully. People would pound stakes down into the ground at the edge of the sea and record where is the highest tidal level during the course of a day and where is the lowest one, and measure the average, and do this in many places around the world. And what they found with these very careful but primitive measurements was a rise in average sea level of about 16 centimeters over 100 years. So 1.6 centimeters, millimeters per year. But since 1992, there have been instruments flying, orbiting the Earth, looking down at the Earth, and measuring the height of the sea level much more reliably, getting a very, very good global average over the whole planet, just looking down everywhere, using LIDAR, laser, height ranging, and another method called interferometry to measure the reflection back of various waves. And so this data set now continues from 1992, where the previous one stopped, all the way up to last month, showing a very good fit to the data, twice as much. Sea level rise, the rate of sea level rise has now doubled. What used to be 1.6 millimeters per year is now 3.2. But there are differences. For example, there's a very interesting one here where the sea level global average dropped by several millimeters in 1 year. And I can remember people saying, well, that proves that climate change isn't happening because sea level dropped. The newest analysis, well, first of all, the best fit to the curve continues to be up, but there's really good evidence now that unusually heavy rains in Australia removed so much water from the ocean, and the water did not flow off into the ocean this particular season in Australia, that may account for this negative excursion. But you'll see that there's not so much a waviness, but a sawtooth pattern, up and down, up and down. But the main point is sea level is now being measured extremely well with high accuracy and precision, a good global geometric coverage, and the rate that's observed is about twice what it was before 1990. Well, another variable that is important is in the Arctic, how much ice is covering the Arctic. This quantity has now been measured very well over 30 years from satellite measurements, and the gray area here shows the plus or minus 2 standard deviations, and this is the 30-year average. So that in the summertime, the Arctic sea ice decreases under the melting, and then it refreezes in the wintertime in the Arctic. However, there has been a great reduction in the Arctic sea ice coverage, so that 2012, which is the lowest at all, was down 4 or 5 standard deviations from the mean. And 2012, you may have heard, 2013, you may have heard that there was a great increase in the amount of Arctic sea ice. Well, that's true. It was up 50 or 60%, but it's still down about 2 standard deviations from the 30-year mean. And the thickness of the ice isn't what it used to be. The coverage is now thin compared to the average coverage before. Now, how would you go about measuring the thickness of the ice? Well, until about 10 years ago, the only source of data was submarine operations. So, in fact, a group of my colleagues obtained some classified data from the United States Navy, and they were able to work with the Navy in such a way that the data could be released without being of any concern to military security. And it showed that the thickness of the Arctic sea ice had decreased about 50% in 50 years. But now there's a new way of measuring the thickness of the sea. I'll get to that in just a second. This is another portrayal of just the coverage itself, not the thickness, but you can see this is the median over the 25-year reference period, and this is what it was in late 2012. So there really are sections of the Arctic which are now navigable. But I want to switch now to the one other measure of the Arctic sea ice extent. This is the long-term fit through 2012, and 2013 was up a little bit, as I say, but it's still following this downward trend. There's a new instrument, though, that's been flying now for 10 years, which can actually measure the mass of the ice on Greenland and the Antarctic continent. Now, what's obviously different about this ice is that if it disappears, sea level will rise, whereas the coverage of the Arctic Sea, when that ice melts, it doesn't increase sea level because it was already floating on the water. But for Greenland, this measurement has shown over a 10-year period now that there has been a rather large loss of ice, 260 billion tons per year on average over this 10-year period, with an accelerating trend of about 30 plus or minus 10 billion tons per year. The best fit to that curve is not a straight line, it's an upside down parabola. In other words, a square law fit, and the acceleration can be deduced from that. This was an unusually large swing where Greenland lost 700 billion tons of ice essentially in a year and a half. The way this instrument works is just fascinating. It is not the way that our grandparents would have made this measurement. They might have had a sextant and a telescope trying to gauge the height of the ice and things like that. This one is measured from Earth orbiting satellites using a laser interferometry to keep the satellite's position locked into each other. They're actually feeling the force of the Earth's gravity as they go around the planet. And let's say a mountain range is beneath. The first satellite comes and starts to feel the mountain range and will be slightly accelerated downward. Then the second trailing satellite can sense the perturbation in that orbit, and after enough orbits, they can deduce what is the anomaly of the gravitational force below that deviates from a perfect spherical Earth, and in that way measure time rates of change. So this record is fabulous because it's actually measuring the mass of the ice, not the horizontal coverage. And then for Antarctica, the data are similar, although less smooth, because West Antarctica is not behaving the same as East Antarctica. One of them is almost always losing ice, and the other one gains and loses. But again, the best fit is a slight acceleration, not just a linear decrease with time. So after about 10 years of data, I think we have to take this seriously. If we had only 1 year of data, you could see that we wouldn't know what to do. But after averaging for 10 years in these two cases, I remember when these data were first released, the principal scientist is Isabella Veliconia, who's a colleague of mine at Irvine. And the first data was only about 3 years, and you really couldn't be sure of it. But now, after 10 years, I think, and all the corrections they've done to the data based on physics, I think is quite reliable. Now, let's ask again from an energy balance point of view, well, maybe the sun is changing. Maybe it's not the greenhouse effect, maybe something else is happening, like the sun's output itself is changing. And there is one error on this slide. It says energy received by the sun. It's energy received from the sun at the Earth. So we now have a 30-year record that has been created by combining the results from a number of satellites which have flown. None of them have lasted 30 years. But it shows that the sun's output has varied almost like an 11-year sunspot cycle. But it's essentially periodic. That is, you come back to the same value every time. Low, 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 high, 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 just about the same. If any of you are keeping track, you will see that this number is exactly 4 times the figure I quoted in that cartoon show of 341 watts per square meter, because there's a geometry factor of basically pi over 4 pi, so it's a 1/4 factor. So we think we're understanding the energy coming from the sun well enough to be able to say that whatever is causing this warming of the Earth, it is not the sun. And that's too bad, because it might have been interesting if it were the sun, and I think some of us wanted that to be the case 20 years ago, but we can no longer say that. Now, there's another very important key climate variable. I've already talked about temperature of the air, temperature of the water, ice amounts, and sea level, all of which are very important, but there are many other important climate variables. For example, the flows in rivers, how much cloudiness is there, and so forth. But I just have the title of a couple of papers here, both of them involving Dr. Chai-Lu and his colleagues, and I'll just show you the 2 titles. But the gist of it is, as temperature has risen, the frequency at which we're getting very heavy rainfalls has increased. And this result is being seen on several continents, although the data that you've shown, you've used a couple of different data sets. One is a global data set, and another one is one from mainland China. And if you just analyze the frequency of rainfall that's coming down in heavy rainfall, it has increased. And both of these papers show that, one of them compared to what is calculated from weather prediction models, and the other one compared against actual measurements. So this is another important climate variable where there is now emerging evidence, which is pretty strong, about the frequency distributions and the rate at which rainfall is falling. Going back to the greenhouse gases now, I've suggested to you that this energy perturbation on the whole planet, which is being caused by the observed increase in carbon dioxide. So if you go back to that curve, what is the observed increase in carbon dioxide over this, let's say, 50, 60-year period? You can calculate from that increase and the spectroscopy, the way carbon dioxide interferes with infrared light, what is the impact on the energy budget of the planet? And it turns out to be about 1.7 watts per square meter. And then if you look at several of the other greenhouse gases, the total number here comes up to be more than 1% of the entire solar constant received by the Earth. Several of these greenhouse gases, carbon dioxide, nitrous oxide, and several chlorofluorocarbons, are stable in the air to the extent that they will survive in the air for more than 100 years before the perturbation is removed, whereas for methane, CH4, the survival time is only about 10 years. So if we had some magic way to start removing carbon dioxide, or I didn't say that correctly. If we removed all of the methane from the atmosphere, that would simulate what the air is doing to itself, cleaning itself under photochemistry in about 10 years, where these other perturbations will last a long time. There is a spectrum of time constants and residence times and survival times of these chemicals, and most of the greenhouse gases are rather long-lived. This subject, what I just called radiative forcing, that is, what is the impact on the energy budget of these observed increase? We're calling it radiative forcing, that is, forcing the climate to change by electromagnetic radiation. It's more complicated than I'm saying today because there's other kinds of forcing going on by aerosol particles floating in the air, often generated by air pollution, and also black carbon, like soot. If you do careful optical measurements now on the snow and ice in Greenland and across the Arctic, you'll find a small black layer of soot and carbon-like material, carbon-containing organic aerosols, which are dirty, and that absorbs sunlight, so it has a heating effect on the surface, things like that. And there are many more greenhouse gases. In fact, a new one was just discovered about 1.5 years ago, nitrogen trifluoride, which is a very inert gas. So that there are really hundreds of greenhouse gases. And one other category of them that I want to mention is the so-called short-lived climate forcing agents. Things like ozone here in the lower atmosphere from air pollution is a short-lived greenhouse gas that only survives a couple of weeks or a month. And if we could remove those, we could get an immediate impact on the Earth's energy budget. We could reduce the greenhouse effect significantly by just removing some of those short-lived ones quickly. But I'm not going into that today. I want to give you a feeling for the amount of energy that we're talking about. The extra heat trapped by those 3 greenhouse gases that I just showed you, 4, is about 2.7 watts per square meter, whereas all the energy absorbed from sunlight is about 100 times larger, maybe 85 times larger. But by comparison, if you take all the energy that humans are using, all of our electric power from coal burning, from natural gas burning, from nuclear power, from hydroelectricity, from wind power, solar power, geothermal energy. If you take all of that energy that humans are using from all of our fossil fuel combustion and everything else and smooth it out over the surface of the planet, it's only 1/40th, 0.025 watts per square meter. So if you wanted to try to warm the planet by burning more fossil fuel, you couldn't do it. The number is too small. But if you amplify that human impact by the greenhouse effect, you get a factor of 100 more. So this is a very effective amplifying effect. It's analogous to catalysis in chemistry, where you can speed up the rate of a chemical reaction by many, many, many times, perhaps 100,000, with the right catalyst in the solution. And here, we're amplifying the way that we can trap heat on the Earth's surface by a factor of more than 100 by using greenhouse gases instead of just trying to burn more energy. Not that we would want to do this, I'm just trying to make a comparison. Now, I've said before, I want to use carbon dioxide as an example now of why we are sure that this is coming from humans. Because if you just looked at these measurements, as beautiful as they are, that doesn't necessarily tell you that it's coming from humans. After all, we can see the influence of photosynthesis and decay in any given year. Maybe there's something else going on that we haven't learned about, like, oh, just as wild guess, some enormous release of carbon dioxide from the deep oceans that might have a 100-year time scale. So could this entire movement be natural? Well, it turns out we have several kinds of evidence saying, no, that's not correct. Let me mention some of it. First of all, a group of scientists internationally led by the French, the Danes, the Swiss, the Russians have taken out ice cores out of these very deep ice deposits in Antarctica and Greenland by drilling down and lifting a cylindrical core and then chopping it and counting the layers of ice and deducing the age of the ice. You get about 1 layer every year, and after you put enough ice on top, it actually squishes very hard, and the pressure causes the ice to flow a bit. So they have to use more sophisticated methods for dating. But they've been able to go back now, it says here 400,000 years. In fact, they've gone back 800,000 years. So 0 here is a present time, you know, the year 2000. 50,000 years earlier, 100,000 years earlier, 200, and so forth. So by pulling out these ice cores and then measuring how much carbon dioxide is in the ice as a function of the age of the ice, what has been seen is that the natural cycles of carbon dioxide, 180 parts per million on this vertical axis, when it was cold, this is the last ice age about 20,000 years ago. The previous one was about 140,000 years ago, and you'll see that the carbon dioxide amounts are about the same when it was cold. 180 parts per million when it was cold, 180 parts per million the previous ice age, 180 parts per million 250,000 years ago, 180 parts per million 350,000 years ago, the 100,000 year ice cycle. When it was hot, like warm where we are now, the natural amount is 280 parts per million, and that can be measured by going back to ice cores that are only 100, 150 years old. And when it was warm previously, 270 parts per million, the interglacial warm period, the previous interglacial warm period, and so forth. Well, where we are now, I've already said, is nearly 400 parts per million. So, whatever is going on to explain how we got up to 400 parts per million, whatever it is, has not happened in the last 400,000 years. So there's something new going on. Now, in fact, I said that this graph has been extended back to 800,000 years. It's a marvelous scientific contribution. There are some Americans involved, but I think the French and the Swiss and the Danes and the Russians deserve most of the credit. So that's one piece of evidence that the carbon dioxide amounts now are not natural compared to the last 800,000 years. Oops, I'm going the wrong way, excuse me. The similar observation for methane. Whatever is causing the methane increase is unprecedented. The normal amount of methane in cold times is 1/3 of a part per million, 1/3 of a part per million, and so forth, back to the previous ice ages. And the normal high amounts of methane were 2/3 of a part per million, and we're now at 1.9 parts per million, almost 5 times as much. So, the statement is that carbon dioxide increase is from human activities, about 85% of it from burning fossil fuels, and about 15% of it, at least in the last 2 decades or so, from deforestation, largely for agricultural purposes. So cut down a forest, then the organic material that was in the soil decays to carbon dioxide, or the burning of the trees makes carbon dioxide, and so forth. Let me give you a little bit more of the evidence. The time history of the carbon dioxide increase that I just showed you matches that of fossil fuel usage. We're using about 150 times as much fossil fuels now as we did 100 years ago. So the time release of the carbon dioxide matches the increase in measured carbon dioxide amounts. The amounts are within a factor of 2. Every year, the amount of additional carbon dioxide that appears in the atmosphere is about, not quite 60% of that released by burning of coal and natural gas and oil every year. Some of it is being buried in the world's oceans. We know that. So to be within 40% of just matching these amounts is very convincing. I already said the 4 glacial cycles. The geographical patterns of the atmospheric carbon dioxide also match the fossil fuel burning. If you find out where are the most polluted areas in carbon dioxide, they tend to be where the fuel is being burnt. The isotopic contents of the carbon dioxide are very revealing. First, we can either look at carbon-14, although that has to be done very carefully to work around the bomb-produced carbon-14, but fossil fuels don't have any radiocarbon in them. They've all decayed. The carbon-14 has decayed. So we can, under certain conditions, we can tell from carbon-14, but mostly we tell from carbon-12, carbon-13 ratios, the stable isotopes. The stable isotopic ratio of fossil fuels is such that it's different from the atmospheric carbon dioxide unperturbed by fossil fuels. So the isotopic contents matter. And then finally, the most elegant of all is a fairly new measurement that's been done for 20 or 25 years now by Ralph Keeling. He has been able to measure the amount of oxygen in air to 6 decimal points using unbelievably beautiful analytical chemistry and physical interferometry. So every one of these dots represents a few hours of measurement at Mauna Loa Observatory, and this is about the year 1990. I'm sorry I cut off the graph to now. And by measuring the ratio of oxygen to nitrogen in air, and assuming that the nitrogen is stable, the amount of oxygen is decreasing. And he's done this at about 10 places around the world. So this is Cape Grim Observatory, 41 south latitude, 20 north latitude. Now, assume for a minute that the only thing happening to the oxygen in air is that it's being consumed when we burn fossil fuels. What would this graph look like? Well, the graph would look like this. Follow the green dot. It's just above where we are now. So it appears that something else is going on. That is, there's something causing, I should have put this graph here, but the actual measurements are about where this green dot is. In other words, above what he's actually measuring. So the rate of loss of oxygen is less than it would be if only fossil fuel were being burnt. We think that's the greening of the Earth's biota, and that some additional oxygen is being released in respiration, but there are even photosynthesis, but there are even other things going on. However, to a first approximation, this downward measurement, less oxygen being measured, is almost exactly equal to the oxygen loss that you would see if fossil fuel burning were the only thing going on. So that's another kind of evidence that this carbon dioxide change is due to human activities. So I think the evidence is very solid for what I said. I'll just mention a couple of other greenhouse gases. This is a very beautiful data set up until this month of nitrous oxide measured in the air at 5 different stations. There's always a little bit more in the northern hemisphere, just like there is for carbon dioxide and methane, indicating again, human activity is what's causing it. But a slower increase, it's not as well understood. But also, if we go back to ice ages, we find significantly less N2O. So there is evidence, although not quite as clear, that nitrous oxide is also from human activities. These are methane data, which I showed 20 years ago. Methane amounts were increasing at a huge rate, nearly 1% per year. It has slowed off now, slowed down, so there's still a slight methane increase, but not as fast as it used to be. This is a really unusual greenhouse gas. It's one of the most stable chemicals that you could ever invent, carbon tetrafluoride. It seems that there is some natural source here which nobody understands, but there are certainly industrial sources that we know about. Largely, the electrolytic refining of aluminum ore is releasing carbon tetrafluoride, but there are other sources as well. It survives in the air for 20,000 years, 30,000 years, 50,000 years. Nature basically doesn't know how to tear this molecule apart once it's released into the air. So, and then there are many short-lived greenhouse gases that I mentioned. So let me stop just by summing up that we have a simple and fundamental physical explanation for the greenhouse effect. And when we add to that the observational data of what is actually changing, the implication is that the contemporary climate change is due to human activity. About the future, I've already said that there is significant uncertainty in exactly how much we're changing the energy budget, largely due to these aerosols uncertainties. We haven't measured them well enough yet. We can't predict very well how long they stay in the air and so forth. I skipped over a point on the very first slide. I'll go back to it in a minute. But in the last few years, the temperature of the air around the Earth hasn't risen very much. So people are referring to this as a hiatus, a pause, like hitting the pause on a recorder. It's as if the temperature increase of the air, that someone has put a pause on it. There's this hiatus. It isn't going up as fast. So one of the leading questions is that hiatus, is that delay, is that pause, is it due to the heating of deep ocean waters? The energy amounts match pretty well, and we know that the ocean has an enormous capacity to absorb heat. Now, we're not in a steady state, we're not in an equilibrium, so as long as we keep adding these greenhouse gases to the air, the oceans and the air will keep up warming, but the ability of the oceans to grab this heat and to sink it depends on ocean fluctuations. So we could see a return to a faster rate of heating, or if even more cold water from the deep oceans gets exposed to the surface, while the weather patterns would change, it could absorb even more heat. I mentioned extreme events just in passing when I referred to the increase in the frequency of very high rainfall events. But it is not yet completely known, is that occurring everywhere around the Earth? It looks as if it is, but it needs a little more proof, and the mechanism of exactly why it's happening needs some more work also, although the simplest explanation and the easiest one to understand is simply that as you heat the air, it has so much more ability to carry moisture, or looking at it from the point of view of a surface of a liquid, as it heats, the rate of evaporation increases, not as a proportional to temperature, but faster than proportional to temperature, the Clausius-Clapeyron equation. So loading the atmosphere with so much more water can make it rain harder. That's one of the possible explanations. And then one of the things we simply have to continue to do is to improve the mathematical models that are solving the equations of this climate behavior from first principles. That is, the people in this field they actually write down the equations of mass conservation, energy conservation, angular momentum conservation, the conservation of materials like water, and try to solve the equations from pretty much first principles to predict some weather changes as well as climate changes. And they're getting good enough now to begin to put some faith in them, but I think they need a lot more work. So before we can deal completely with the social adjustments we're going to have to make and economic adjustments, we would like to have more predictive capability. On the other hand, the reality of this effect is so large and it's so well connected to human activity that I think we have more than enough evidence to try to mitigate the changes, that is, to slow them down at the same time. So I think I should stop there. I've gone on long enough, and I hope we have time for a little discussion. Professor Wang.
Next is a time for discussion. So our President Wang will host this session, and our colleague will help setting the chairs and tables. Please wait 1 minute.
So thank you very much for the wonderful lecture. I think we have some time to take questions. I cannot see the audience. The light is so bright. Okay, yeah.
I guess the question I have is when you measure the CO2 level in the atmosphere, you see this annual fluctuation. So it's up and down, and that's usually explained as the annual fluctuation in photosynthesis. I'm here. Okay. Yeah. So the CO2 annual fluctuation due to photosynthesis. But at the same time, you also see the oxygen level fluctuation. This could be also due to photosynthesis because one CO2 molecule fixed, you would generate one molecule of oxygen. So when people actually did a simple calculation, do these two fluctuations match? If not, maybe the oxygen fluctuation is due to something else in addition to photosynthesis.
Yeah, the oxygen solubility. The solubility of oxygen in water is a strong enough function of temperature that a lot of those annual changes in oxygen are simply the changing equilibrium of ocean surface water. That is what. So to relate the oxygen change to the carbon dioxide change probably requires a couple of years of everything, because I think you're right. Those fluctuations are not newer.
I see.
And we also have seasons different around the world. With northern hemisphere photosynthesis occurring 6 months off of the southern hemisphere and some ocean hemisphere. So it's a little more complicated, but averaging over several years, you can see the comparisons.
Yeah. If I could ask another question.
The other thing is,
Okay.
what's interesting is how much carbon dioxide is removed
Mm-hmm.
from photosynthesis. So
Yeah.
I'm fond of thinking of cornfields in the middle of the United States where the corn is grown. If you look at a growing season for a crop like corn and ask how much carbon is in the plant, it would have required all the carbon dioxide pulled out of the atmosphere 10 times.
Mm-hmm.
So there's always new fresh air being brought in. Tremendous amount of carbon dioxide being pulled out during photosynthesis. The numbers are huge.
Yeah, so this probably leads to my second question. So if you look at the fluctuation due to photosynthesis, that's still pretty small compared to the overall increase of CO2. Let's assume we could double the vegetation on Earth. Even with double, that's very difficult to do. That's not going to change the overall picture that much. So that's a very discouraging situation, in my opinion. I don't know whether this is a correct estimation, or maybe I should be a little bit more optimistic.
And it's even worse because photosynthesizing plants do not photosynthesize proportional to CO2 amounts, the difference between C3 and C4 photosynthesis. One of them essentially is the square root of the carbon dioxide because it's diffusion limited. So it's even worse than you say.
Wonderful talk. I think I'd just like to do an advertisement for the NAS and the Royal Society. The two societies have put out a wonderful booklet, which we hope can be translated into Chinese and Hindi and other languages. And I hope the societies will do that, allow that, give that permission. But one thing I learned from looking at that booklet I had not realized before was that the models for greenhouse effect predict, of course, warming in the troposphere, but cooling in the stratosphere. And that has been seen, and that's easily understandable to astronomers between the difference between optically thick and optically thin regions. But it really rules out, crazier ideas such as solar incidence or galactic cosmic rays. Would you care to comment on that?
Yes, Professor Shu's absolutely right. The way the greenhouse effect works is that every molecule that's in the air is constantly absorbing light and radiating light. And as you go higher and higher into the air, the radiation to space is a larger fraction than, what am I trying to say? You get a net escape to space, whereas a molecule buried lower in the atmosphere is receiving almost as much from below and above. So you got a very effective cooling as you go up in the air, and a signature of the greenhouse effect is that the air should become, with time, colder and colder as you go up. And astronomers understand this very well because of your radiative transfer experience. So it is a signature of the effect. It's a fingerprinting. And it has been observed. An interesting aspect of that is as the upper atmosphere cools down, and I mean really high altitudes now, 300 kilometers above the Earth, as the greenhouse effect gets intense, that air will cool down even further. So the frictional drag on Earth orbiting satellites will be reduced.
Thanks for the wonderful talk. Your data are really very astonishing. And I noticed that your early slide show the increase in temperature starting almost about 1960, almost linearly, right? And it matched very well with the first Green Revolution that occurred during the 1960 to 1990. That during that period of time, the crop productivity doubling and human population are doubling, but the land use is only increased by 20%. And so the increase of population, of course, will contribute to the increase of greenhouse gas, but it's probably either from both industry and agriculture, because the Green Revolution, the crop increased mainly from improved technology in growing wheat and the rice. But during the period of time, the increase of rice, we expect it will be increase of methane from rice paddy, because it has been estimated almost 1/4 of methane is emitted from rice paddy. So to control the agriculture activity probably is important. I don't know how much have been contributed from industry or from agriculture for the increase of temperature. But now the problem we're going to face in the next several decades is the world population is projected to increase from almost 7.2 billion to over 9 billion by year 2050. And I don't know whether the activity from industry will saturate to a certain point, but from agriculture, it is expected will be increased, because we need to increase at least by 50% of crop productivity in order to feed with this increase in population. So what comment you're going to have to on this, particularly for people like us working on agriculture, and how we could improve agriculture to control such a greenhouse emission from agriculture activities?
Well, we definitely need more scientific work, because I think let me take one of your examples, that is human population and demand for rice and methane release into the atmosphere. I think that is a big cause of the methane increase that's been observed. And it's not just due to more planting of rice. I mean, as you said, the amount of arable land being used has not increased as much. But double cropping and triple cropping of rice has led to much of the extra rice production. And from the point of view of microbes, bacteria that produce methane, methanogenic bacteria, they are very happy, because now they are in anoxic conditions 2/3 of a year or one entire year due to triple cropping. Whereas previously, before double cropping or triple cropping, they could only produce methane 3 months a year or 4 months a year. So more production of rice has definitely led to more methane in the atmosphere. And to understand that, you have to understand methanogenic bacteria and everything that goes with it. With nitrous oxide, it's not so clear. It seems to be traceable to the use of nitrogen fertilizers. Rice is not very efficient in using nitrogen fertilizers, as you know, and neither is corn. So there's a lot of loss. But so we have to go into these details to understand what is the link with human population, what is the link with human dietary consumption with the environmental effects in this case. I think we have to understand each element's processing very carefully. It's not directly related to population necessarily, but it's certainly a driving force. Population is a driving force.
I hope it's okay to ask 3 questions instead of 2. The first is you talk about the photosynthesis and the release of oxygen and also consumption of CO2. NASA has been measuring these world distributions of algae over the oceans. Do you have any new data to show that it's increasing or decreasing at this moment?
Aware that the measurements are quantitative enough to make relative change measurements. It could be, but I'm not aware of it. But by sensing chlorophyll A from space.
Right.
Yeah. I don't know if those measurements are quantitative enough. They might be, but I'm not sure.
Okay. Well, the second question is about the hiatus. You just mentioned a little bit. There are actually a few more theories about what causes that hiatus. And one is that since the Montreal Protocol people has stopped emitting some of the greenhouse gases, those CFCs, and that may have contributed some. And we recently worked on a theory on the coupling of ozone and the water vapor in the stratosphere, and that seems to also work in terms of time-wise. And so this may more like a comment rather than a question. I know that problem is not really solved at this moment. Okay, so the third question is, you have not touched upon a sort of dangerous idea that Paul Crutzen has been talking about, this geoengineering in mitigating the global temperature. Do you care to comment on that a little bit?
There have been a number of ideas proposed in the last few years about how to intentionally engineer the Earth's environment to slow down climate change. And one of them, which is now seen to be reasonably gentle, would be to fertilize the world's ocean. There are parts of the world's ocean where the limiting nutrient is iron rather than nitrogen or phosphorus. And with a very, very small addition of iron to the surface waters, you might be able to increase photosynthesis to grab carbon dioxide out of the atmosphere and somehow slow down the buildup of carbon dioxide. But the only way that can happen is if the carbon is buried deep in the oceans where it will not be able to re-enter the atmosphere. And the experiments that have been done show that the increased photosynthesis leads to a buildup of algae in the surface waters, but that the carbon is recycled in the surface waters and then released as carbon dioxide very quickly. So that idea does not seem to be too good, although it hasn't had enough research. But the one that Paul Crutzen, of course, has restated and brought about again is the intentional injection of material into the upper atmosphere where it can form sulfur-based aerosols, little reflective, highly reflective floating particles made out of sulfate, which can reflect sunlight back to space. So it would be as if we have a dimmer sun by, for example, producing a sunlight which is only 98% of what we receive now. We might be able to cool the planet. This one could be more dangerous because we don't really know what would happen. And even if it works, even if we could prevent the climate from changing, as long as we continue to use fossil fuels, the air will get more carbon dioxide, and that makes the oceans more acidic. So we would continue towards ocean acidification, even if it would work. There's very little research going on in this field. In the United States, our government doesn't really support it, even allow the research. I mean, there are a few. The Gates Foundation is paying for a little bit of the research, but not very much is going on. The people who used to work on weather modification think it's a very bad idea.
You talk about the retrospectively what happened for the past either decades or thousands of years, and you taught us the trend, and including myself, I don't think we appreciate enough for what's going to happen in the future if this trends continue to do. Some of us say it's going to raise the ocean water for 3 meters, others saying it's only 4 centimeters. And some people say we're going to heat ourselves to death. And others are saying, well, it's going to feel a little bit hotter. We just turn on the air conditioning. Would you comment on, to your expertise, how should we visualize our danger in a realistic and say in the next 50 years? Thanks.
The driving forces are, some of them really are linked with population. Others are linked with energy usage and fossil fuel consumption. And there, the figures are really very frightening. The world increase in fossil fuel burning is continuing. And to meet the energy demands of let's say, the 2 billion people on the earth who are poorest and who do not have electricity, it's going to take an enormous amount of energy. And whether you look at it from an ethical point of view or simply a practical point of view, it's not possible to stop that. The demand has to be satisfied. So we have an enormous energy challenge on our hands, which is going to lead to more CO2 in the atmosphere. And whatever the climate impacts are going to be, it's just a question of how quickly they arrive. So sea level change, due to the melting of Greenland and Antarctica, is one of the worst ones because it's irreversible. So in evaluating the seriousness of these problems, I think we have to distinguish between fast and slow and irreversible and non-irreversible. And in the case of sea level rise, it's not reversible on any human time scale. The geological evidence from people who study sea level rise is that there have been periods of fast sea level rise. And the current estimate on how much sea level will rise during this century, some of you will still be alive at the end of this century, varies from about 0.5 meter to 1.5 meters. But we're not sure. It could be more. So then how quickly can humans move in a disruptive situation? How quickly can they adapt? If it happens in 30 years, we're in extremely serious trouble. If it would happen in 300 years, people might be able to adapt. Another kind of irreversible change is the extinction of biological species. Once we lose biological species, there's no reversibility, at least not yet. I mean, there are dreams of reconstructing organisms from stored DNA, but these are dreams. So in evaluating these risks, until we have perfect climate prediction, which will probably be never, we have to make some judgments. And I think the problem is really quite serious because of the forcing factors being so closely connected with human development.
It looks like there's no sense of urgency. Particularly if we look at the last 10 to 15 years, there are a lot of talks about how to control the situation. But if you look at the way you show, everything's still going up. The only thing going down is oxygen. And then also new greenhouse gases coming up. Carbon tetrafluoride and nitrogen trifluoride. I wonder where is the nitrogen trifluoride from?
Synthetic using in the electronics industry. Yeah.
So the same as carbon tetrafluoride.
Totally synthetic.
Is there any question from the high school student? Yeah. So about your future?
Yeah, sorry. As a matter of fact, we do have a question. So we're from Taipei American School. That's the high school you're first to. Hi, everyone. So I have a question, and that's assuming that we cannot curb in the near future the use of fossil fuels, and so global warming continues, and we aren't able to mitigate the effects of global warming, is there any way within the next 50 years we can perhaps adapt to the increase of temperature around the world?
A bunch of sensible strategies, each one of which will help, and all of them have other purposes. Let's start with energy efficiency. We are, for various reasons, wasting a lot of energy. Some of it because our technology can be improved. We have other ways of wasting energy. We can have enormous gains by using energy more efficiently. And I mean, on average, 30% for the whole world. Better insulation, switches which automatically, kill appliances when they're just on an idle. It's called vampire energy that's being used by an appliance that looks like it's turned off, but it's not. As I said, insulation, automobile efficiency, electrical power plants, where we would save money at the same time. So that's the kind of action where we can have more than one benefit and also slow down climate change. Adaptation, though, I think needs even more work because we know that climate change is happening, and there are some actions that we can take that will allow us to adapt to the changes while also making other improvements. So, for example, in water management, one of the big concerns is that the more intense precipitation will cause more water to run off and be lost or to do damage along the way. We can have better water storage and guidance facilities also to bear over times of drought. So adaptation, building things near the ocean which can survive higher sea levels and storm surges, hoping that it's not going to happen too rapidly, but being able to deal with something, let's say up to 1 meter, would make sense for other reasons. So there's a lot of good things we should be doing, and many of them have double benefits, and you probably have some good ideas too. In agriculture, I think we simply must develop crops which are more tolerant of floods and droughts and temperature extremes and salt, so that perhaps slightly more saline water can be used for irrigation in those times of necessity. And that requires people to become comfortable with the idea of genetic modifications of crops and to do the work very, very well, very safely. So it's going to require tremendous science and tremendous understanding of the possibilities in the general public. That means education.
Great, thank you.
Ralph, you have convinced us that the energy balance is really determined how temperature rises. And you also mentioned greenhouse gases is the one which really determine the energy balance. So the way it looks, the business as usual, we keep on going. Within the next 50 years, we'll be in a very, very miserable situation. And I think at that time, we will not be here. I say we, it means you and I will not be here, but the young people will be here. And we have been pushing a global program called Future Earth and try to understand how the Earth are changing, how can we prevent the change, and try to understand all of those. But I become very pessimistic. We try to understand what's going on, yet things are going on continuously. And we said by 2015, in the meeting of Paris, if we do not come to some agreement for the adaptation, and we don't have future. But today, when I face the young people, I have to be very apologetic that we are not doing enough, or the way things are going, the EU will not have future. And so, we still work very hard. So something beyond science. We have to control population, consumption, we have to make drastic change, and that's not happening. And I feel very sorry. I've been serving as the president of International Council of Science, and for the last 5 years, we thought we are working very hard, but nothing are really changing. So I don't know, can you suggest something that we can do?
I think you've done some amazing work. I think you're helping to convince very important people in every country that this challenge, we cannot run away from it. We just have to work on it. And I think you're convincing a lot of people. More people are talking seriously now about adaptation and realizing that whatever the causes of what's happening, we have to be prepared, and that many of the strategies are what we call win-win. You can do two productive things for the price of one. So I do see some progress. And I think on energy efficiency, we're making very fast progress. So am I happy? No. But I think good progress is happening.
I do believe one thing we can help. And if we accept that the entire Earth is overdeveloped, or human society is overdeveloped, then there's no sense for something called developed country try to help developing country. If the country is overdeveloped, then we have to accept the fact even the society like Taiwan is overdeveloped. So we said that's not the way to go. So in Asia, we have to find a new way of development, entirely new way of development. And so there's some common sense that we have to develop differently. And we have to change our lifestyle. For us, we say we have to sacrifice. But that's really not a sacrifice. We just go away from the stupidity, maybe. Anyway, so it's really very serious.
Thank you.
My question at your next talk. But I think one of the problems why the world has made so little progress and why we see so much pushback from people who should really know better. I mean, I've just raised one of the prime examples, the Koch brothers in the United States, who are behind much of what we would call climate change denial. These are smart guys. One of them was ahead of me at MIT. One was, I'm ashamed to say, behind me at MIT. These are PhDs in chemical engineering from MIT. I don't believe that they don't cannot follow these arguments that climate change is happening. I think instead, they do not like the answers. They do not like the solutions that are being proposed. It's not that they don't understand the problems. And that is a problem that's not scientific, it's social, it's political. They speak with one voice, it's incoherent, but it's one voice, the opposition, and scientists don't. And in some sense, we have to transition to a period where we talk amongst ourselves more and really offer solutions that seem acceptable to not everybody, but at least the majority of society.
I knew the Koch brothers when I was a student too. They're ahead of me. But without personalizing it, I think you're right that many of the public discussions you hear about climate change, the heading will be "the science is wrong" or "I don't believe the science," and then you read what or listen to the person, and they're really talking about the responses. They're talking about different values and how to deal with the problems. So the science is becoming really more and more solid, and that's what I spent my time on today, just to show you real data rather than all theories or modeling calculations. It's really becoming very serious. But the public discussion is mostly about what responses to make. If you were the king or the emperor, one of the questions you would have to ask yourself is, what are the costs and what are the benefits of various actions? And there is not much disagreement. I mean, there are political disagreement, of course, and ideological ones. But when economists try to estimate the costs, for example, of the business as usual scenario that Professor Lee mentioned, they don't get the same answers because the climate scientists and meteorologists have not yet made good enough estimates of all the costs, and some of them are so large that we don't even know how to estimate them. For example, what is the cost of losing biological species? How do you put a value on that? We don't know how to do it. And when they try to calculate the benefits of, let's say, investing in something now, spending money, you have to compare the net present value of that money with what it will be worth 30 years from now. And that requires a discount rate assumption in economics. And one of the prime examples of this was a report in the UK in, I think, 2007 from Nicholas Stern, a very, very big, thick report called the Stern Report, where he assumed a different discount rate on an economic calculation than all the other economists did. And he showed that it's worth everything that we can spend now to prevent climate change. But many economists disagreed with him so strongly. And this is now on a technical judgment, not just a value judgment. So we have a lot to do on how we value future benefits against current benefits and whether or not an investment is worth money. So there's a lot to do, even in the academic world and the business world, that is not so much moral or value judgments, but how to make estimates, I think.
Okay. Because of the interest of time, we have to end the discussion here. Thank you so much for the wonderful lecture to make us aware of the serious problem we have mentioned. Please join me to thank Professor Cicerone.